Okay, let's take a look at 135J. In 135, we are looking at power series, and we're asked to find both the radius and interval of convergence. One thing about this power series, it's called a power series again because we have this variable x, in this case x plus 1, raised to the nth power. So that's why it's called a power series. And the question is, the interval convergence will be what values of x make this series convergent? When we see this x plus 1, you should recognize that we say that this is centered about x equal -1, because clearly if x is -1, I get 0 here, and I'm just adding a bunch of zeros up. So this series is clearly convergent. Sum would be 0. And so we're always convergent for power series at the value of x we are centered, we say about. Okay, so the question is, what about values of x not equal to 1? So I'm going to use the ratio test to see if I can determine the values of x where this series converges. And in fact, converges absolutely. So I look again, remember, at the ratio of a sub n plus 1 divided by a sub n. I like to think of that as a sub n plus 1 times the reciprocal of 1 over a sub n. So we have, if I do replace n with n plus 1, notice n plus 1, and then replace n with n plus 1, I get n plus 1 plus 1 or n plus 2. All right, so I'll have -1 to the n plus 2, x plus 1 to the n plus 1. I'm replacing n with n plus 1. And then again down here, n plus 1 gives me n plus 2. And then the reciprocal, 1 over a sub n, is just the reciprocal of this expression, n plus 1 divided by that stuff. Notice x plus 1 to the n plus 1 power is x plus 1 to the nth times x plus 1 to the first. Remember, we're adding exponents when we multiply. So I can divide numerator and denominator by x plus 1 to the nth power. Also, when I take the absolute value bars, I'm just going to get rid of these -1 to the n plus 2 or -1 to the n plus 1. Not going to worry about canceling or anything, but because it's the absolute value, these will always be positive. So I'm just going to get rid of those sign changers, right? So what I'm left with is 1 times n plus 1 times this x plus 1, and then down below n plus 2. Okay, now when I take the absolute value, I'm going to go ahead and take the n plus 1 divided by n plus 2 out of the absolute value bars because they are always positive. But the x could be something that such that x plus 1 is negative. So like if x is -2, -2 plus 1 is -1. That would be a negative value. So I need to keep that in the absolute value bars. I'm going to actually pull that absolute value of x plus 1 out of the limit because the limit says n is going to infinity. So x is really a constant with respect to n. So it's like a constant multiple. I can pull it out here. All right, but I keep the absolute value bars around it because, again, x plus 1 could be negative. However, n plus 1 divided by n plus 2 are always positive. I hope you see that the limit as n goes to infinity of this ratio is clearly 1. You can apply L'Hopital's rule and get that immediately. So basically, we have then the absolute value of x plus 1 times 1 is our limit. And now this must be less than 1. Why? Because we're using the ratio test. Remember, the ratio test says if this limit is less than 1, then the series will be convergent. So I know that x plus 1 must be less than -1, or saying what x plus 1 is between -1 and 1, or if I then subtract 1 from every side, if you will, or all three values here, I get -2 is less than x is less than 0. So that tells me the radius of convergence is 1, right? Because we're centered at -1. I'm going 1 below -1 and 1 above -1. And these are the endpoints of our interval. So the radius convergence, we call that capital R, or right capital R, is equal to 1. What about the interval of convergence? Is this it? Well, no, we need to check these endpoints. And that's where we've been spending so much time looking at how to determine whether a series converges or diverges. Now this is going to apply that skill to put that skill to the test. Okay, now let's check the endpoints. We're going to check at -2 first, which is the trickier of the two endpoints. If I plug in -2, and again, where am I plugging in? Go all the way back up to the original thing here, right? So the only thing, this is all the same. I get -2 plus 1. That's -1 to the n power, right? -1 to the n power. And so that's what I get. I get this. When I replace x with -2, I get this extra -1 to the n up here. Now be real careful here. When I'm multiplying like bases, -1 and -1, what do we do with these exponents? We add them, right? N plus 1 plus n gives me n plus n, 2n plus 1. All right, so I get -1 to the 2n plus 1 power. Now you might think, oh, hey, I've got an alternating series, and so it's convergent by the alternating series test. However, be careful. -1 to the 2n plus 1 is always going to be -1. Why? Because 2n plus 1 is always odd, right? 2n is always even. So if I add 1 to an even number, I always get an odd number, right? So it's always odd powers of -1, right? When n is 1, we get, or when n is 0, we get 1. So -1 to the first power is -1. When n is 2, we get, or when n is 1, I get 2 plus 1, I get 3, -1 cubed. When n is 2, I get 4 plus 1, 5, and so on, right? So it's always odd powers of -1. So this is always equal to -1. It's not changing sign. It is not an alternating series. If I factor out this -1 multiple, right, then I'm looking at the series really of 1 divided by n plus 1. You know, let's just focus on that, right? The positive term series there, 1 divided by n plus 1. Well, that series diverges. You can either use limit comparison with the series 1 over n, right? The harmonic series, the p series with p equal 1 that we know is divergent. It's very easy to show from that using limit comparison that this corresponding series diverges. Or you can also use the integral test. You can look at the integral, in this case from 0 to infinity, of 1 divided by x plus 1 and show that that integral diverges. So either way, make sure you check that, but that should make sense. When you're doing these problems, I would like you to state what test you're using, right, to determine the convergence or divergence of this series at this endpoint. So since it diverges, we're not going to include x equal -2. We're not going to include that endpoint. What about at 0? Well, if I plug in 0, let's go back up to the formula here. 0 plus 1 is 1. I get 1 to the nth power, which is always 1. So it's just 1 times this. So I just get this. This is power series when I plug in x equals 0. And if you look at that, then that indeed -1 to the n plus 1, as opposed to -1 to the 2n plus 1, that will indeed alternate between positive and negative, because n plus 1, is going to be, n equals 0, it's 1, n equal 1, it's 2, and then 3 and 4. So this is bouncing back and forth between +1 and -1. But this converges by the alternating series test, because 1 divided by n plus 1 is going to 0 as n goes to infinity, and it is clearly decreasing. So we are going to include the endpoint x equals 0 because we get a convergent series. We are not going to include the endpoint x equal -2 because it is divergent. And so the interval, notice we use interval notation. I'm going to go again and not include -2. So I use parentheses, comma, 0, include bracket. Okay, if you want to use inequality notation, that's fine. You would say x is what? Going to be greater than -2, or -2 is less than x, but at the same time, x is less than or equal to 0. Okay, that is the interval of convergence and for this power series.